So I think in the interest of time, so there's no Q&A here, but I would like to go to the next speaker. It's Paolo Faraboschi. So he was also involved in the early years of HiPEAC. So he graduated from the University of Genoa, I think, in '93. So before the break, this is people with gray hair or no hair, as you will notice. We will have the younger people after the break. And then he moved to HP in the United States, in Cambridge, Massachusetts. But then he came back to Europe from 2002 to 2014 to run the HP organization here in Barcelona. And that's exactly the time when HiPEAC was created, and you were also part of that effort. Unfortunately, then he moved back to the United States, to Palo Alto in 2014, but we are very, very happy that you are here today to give your perspective on what happens here in Europe in HiPEAC. The floor is yours.
Thanks, Koen, and it's an honor to be here, and I have to say that I think Christina will talk about that in her remarks later, but I was one of the people that managed not to kill HiPEAC in the first years of its life, because I was one of the reviewers for the project early on, and you know, of course, I loved it so much that, you know, I clearly supported it. So Koen asked me to give a little bit of a retrospective and then looking forward. So what I'll do here is I'm going to talk about effectively the role of the innovators, which is, you know, this community is all about innovation across different boundaries in times of change, right? I mean, the last 20 years, we've seen a lot of changes in the computing landscape. And I'm going to talk about, you know, 4 waves of computing, plus, you know, the new wave coming up in AI right now. And, you know, the role of the innovator is always tricky, right? Because you don't know that there's a wave until the wave has already hit you. And you typically have, like, some visibility on certain things. If you're the early market mover, you can have some advantage, but then, of course, you know, there's the hype, and then, you know, we have to be able to, as the picture of the, you know, famous, you know, elephant and the wise man, you know, Indian kind of tale says, you know, you have to be able to spot the forest from the trees, right? You typically see hints, but you don't have the full picture until the things have already happened, right? So I'm going to tell you about, you know, 4 projects that I was involved in and 4 waves that corresponded to 4 waves. And then, you know, starting from kind of where HiPEAC started, you know, a little bit before that. So, and, you know, I'm going to use some quotes and tell you some of the waves, right? The first wave that I was involved in was actually kind of writing the Moore's Law acceleration, right? So this was late 90s, end of the century. Lots of new technologies were coming in from the high end into the media and embedded space, right? So people were building new systems, you know, think about digital cameras, you know, printers, set-top boxes, all the digital revolution of media. And they were building horrible computing systems to deal with them. You know, lots of ASICs and you know, pretty much every project that I've been involved in early on had an ASIC crisis where everybody was kind of delayed by years because, you know, they couldn't put things together. At the same time, you know, the Moore's Law was making compute from the high end, the micro supercomputer, you know, techniques like VLAW and ILP, very accessible because, you know, it was a very fast acceleration, right? So what we tried to do here was basically taking supercomputing technology, which you could find in something like a VLAW engine, very high end, and move it into an embedded system to do media processing, right? So this was the first project that we started at HP Labs Cambridge with, you know, my you know, supervisor at the time was Josh Fisher, who many of you know. And what we did was basically say, hey, can I use supercomputing technology, shrink it into an embedded processor so that I don't have to live with the horrors of building these complex systems, and I can just effectively, you know, widen my ILP and create something that can run, you know, all sorts of stuff, right? So this was actually a very successful project. You know, we ended up building, in partnership with STMicro, a family of VLAW processors that ended up in, you know, hundreds of millions of products. I mean, if you, you know, for those of us old enough, if you ever owned a digital camera, a set-top box, or, you know, a DVR in the 2002 timeframe, chances were that you had one of those or more of those cores inside. Now, that was kind of interesting because, you know, we learned a few things. So I'm going to tell you in these waves is what we learned, right? The first thing we learned was that it's not as simple, right? You think, okay, I got a research lab, I got a product. What I do is, you know, I transfer it to my product units. No way. right? It didn't work that way. So we had to invent this kind of, we call the hairpin path, you know, the hairpin meaning you start from research, then you gotta find a partner, and then that partner develops the technology, productizes it, and then your products buy it back. And that's probably very common also in other areas of research because as someone told me, if I get technology from my own research group and something goes wrong, I don't know who to sue. And so nobody likes that part, right? So that's why we had to kind of find a partner, in this case with STMicro, and do that, and find ways to deal with it. Now, the other thing that we learned is that obviously when there's a new technology, people are gonna use it in a way that you had no clue, right? Remember I started by saying, hey, we're trying to simplify the way in which we build SoCs and you know, complex chips. So you can make it wider. If you need more computing, it's a VLAW, so you can just double the width, right? Nope. Engineers, once they figured out they had a core, they kind of rubber, you know, stamped it 5 times. I need more capacity, more compute capacity to do, you know, some other algorithm, take another core and put it in. So we ended up with parts like this one here that had like 5 different CPU engines, you know, 2 different, you know, VLAW engine, one doing codec, the other one doing anti-counterfeiting, the other one doing video or audio, which was kind of against what we thought, but hey, it worked. So, you know, necessity is the mother of invention. Once you have something, you never know, right? So the second wave I want to tell you about is the opposite direction, right? So now, you know, 2005, right? The iPhone was born in 2006. So now we're in the opposite scenario. Now there's a lot of embedded technology with high power, right? High computing power, I mean. And so you know, someone has said once upon a time that, you know, if you round off the fraction, embedded systems are 100% of the production of microprocessor in the world in those days. And it's probably still true today. So what we then wanted to do was the opposite, right? So now we shrunk a supercomputer into an embedded system. Now, because now mobile systems are everywhere, can we use mobile systems to build servers? Because those were low power, extremely customized, you know, you don't need all the stuff that, you know, comes from the PC world to build a server. So what we did was effectively do, it was called Project Moonshot at HPE, and was kind of taking the idea of using SoCs that came from the mobile world to build a new family of servers. And the transition here, that sort of the wave was like the wave of mobile servers, which intersected the wave of the internet growth, right? Because now you were serving gazillion web pages, and you didn't really need the, you know, the full set of features in a server to serve those, you know, web pages and do that kind of, the kind of internet traffic. So, you know, we started building something which was an extremely dense product with like 48, 45, you know, server blades in a single 4U chassis, which was very revolutionary. We're also able to kind of use a lot more things. We're the first one ever to build an ARM-based server using, you know, a 64-bit ARM processor in 2009 or something like that, right? So this was long before, you know, the ARM then became important. And so this was sort of, again, the second wave. Now, the first one was, you know, shrink supercomputer. Now, you know, take mobile, turn it into a server, right? We learned a few things out of this one. First of all, you know, yes, you got to show that you can actually use this stuff on your own technology. One of the most interesting testimonial here was the fact that we were able to serve our web pages using Moonshot. We also learned that sometimes, you know, if you go out too early and you got a lot of attention, they're going to hurt you because, you know, you have too many expectations and so on. And also we learned that if you're too greedy and you try to make too much money early on, you can kill products very easily. So this was an example of a project that, you know, we kind of saw the wave. I think we did we had some great ideas, but it didn't quite work out. Now, many of the folks that work on this project have then moved on, and they're all kind of doing the same thing within the hyperscalers. I mean, many of the folks like Partha and so on are now at Google or some of the other hyperscalers, and I'm pretty sure they've, you know, applied, or at least based on what they say, some of the technology here. So, third wave that I want to talk about, this is the wave of the big data era, right? So now, you know, first wave was, again, Moore's Law, shrinking supercomputers. Second wave, you know, the rise of the internet. Third era, the rise of the big data, right? Now we had, you know, massive data processing needs. We're talking about the era around, you know, 2012, 2013, 2016. And the problem that we had was that, you know, this convergence of the 3V, the velocity, the volume, the variety of the data was causing a lot of complexity, right? Because you had like 20 tiers of memories, from memory to storage. You had to use different abstractions. You had to kind of, have persistence in one place, deal with DRAM, deal with speed, and so on. So we had the idea at the time to say, can we simplify that? Is there a way to effectively think about this as just one memory space? I mean, the idea is powerful, right? I mean, it's like, I don't need to worry about, where am I putting it in the memory tier? Do I need to persist it or not? We also had line of sight on technology, the whole non-volatile memory, that had the potential to effectively break this memory hierarchy. And we were playing with the idea of having like one universal memory tier that had both persistence, speed, bandwidth, anything you needed. And we're trying to build something that could take advantage of that based on our technology was Mesmerister. And that's when we came up with the machine project. And the machine project, I think, was also a very interesting idea because we were trying to combine effectively the scale up and the scale out world, right? So in other words, if you have like one single tier of memory and you have very fast interconnects, you don't need to worry about all of that. And so we built a prototype, with effectively a petabyte of memory in a single rack, and we built all the software to be able to deal with it. Unfortunately, something we learned is that you should never, ever try to compete against flash and DRAM, right? I mean, and this is a picture of like an L register, kind of article when, they talk about Intel that finally decided to kill Optane after nobody was buying it, and so on. I mean, the problem is that, we were hoping for these new memory technologies that had the potential to be really disruptive, except that, when you pick memory and you look at the fundamental properties, you need to have speed, endurance, and cost, and you only got to pick two, unfortunately. We were hoping you could get the three of them, but no, you really only have to pick two. And so you were kind of a little slower than DRAM, a little cheaper than flash, but by the time DRAM got cheaper and flash got faster, they basically squeezed these technology, which had no future, and nobody, it's not just us, figured out a way to do it, right? And so, also we were thinking about, okay, if I can target a single unified memory space, it's better. Of course it is. I don't need to worry about persistence, except that in the world of software, if you already have something written for databases and persistent layer and so on, better doesn't mean winning, because you still have to rewrite the code for this new memory layer, which I think at some point will come up, but that was clearly too early. So this was an example of, I think it was a great idea. There was a lot of good technology. We were developing Gen Z, which was the kind of this combined scale up and scale out interconnect technology, which ended up effectively influencing, and a lot of that technology merged into CXL, which is still something that you can find today, but it's still not quite there yet, right? So I mean, we're kind of ahead of the game on this one, but I think at some point, hopefully, some of these things are going to be moving. The last wave I'm going to talk about historically is the exascale wave, right? So this has been a decade of work. And many of you were involved in the early days. We're talking about, from the 2010, when people were looking at the evolutionary path, the revolutionary path. How are we going to get to effectively an exascale, an exaflop of 64-bit? I mean, this is real flops, right? Not the I-flops, the 4-bit, 8-bit. These are like 64-bit flops in 20 megawatts, right? This was the big goal that, the whole exascale community set up. And, and it was a powerful idea, right? Because at that time, effectively, if you added up all the top 500 computers, they would basically add up to one single exascale machine, right? So we ended up doing a lot of work to develop the core technologies, starting from the system architecture. These are extremely complex systems. Managing them and, dealing with cooling, dealing with the topologies, dealing with the networking is extremely hard. And I know Matteo said that, yeah, we don't want to compete in the top 500, but we do, right? Because there are actually new science that is enabled when you can get to the real next level of computing performance based on what our customers are telling us. And so, the US in that case had, I think, the good idea of, starting with a broad set of vendors and then over time narrowing it down to like a few, so that they could develop and help the foundational technology, not just on the chip side, but on the interconnect, on the photonics, on the way in which you connect the I/O system and so on. Also, and again here, it was interesting because we ended up actually building, and Matteo showed up the top 500 list. We ended up building the only 3 exascale machines that have been published so far. LCAP was the last one that was announced in the latest supercomputer. It's like 1.8 exaflops. But it didn't go exactly as planned. So something we learned in this wave was that there were external forces, like, for example, the US accelerated the procurement, which we were hoping to get into the 18, 19, 20 to 17. And so, it kind of, nobody had the energy to effectively put together all the technology was needed to hit exascale in time. And so, we ended up effectively joining forces with Cray because, we couldn't develop the technology. Cray couldn't scale the operations. We had this target of hitting exascale in 22, in 21, which we actually ended up doing, with Oak Ridge. And it was a completely different way, but what I'm trying to tell you is that the innovators, sometimes, you gotta look at different ways in which you're doing with things, right? You gotta look at, ask for help, right? In this case, it's like, clearly, none of us would have made it alone, but, the minute we joined forces with Cray, it became possible, and now we have the only 3 machines out there that actually broke the exaflop barrier. And this was a lot of work, right? I mean, these machines, we're like 150 kilowatts rack. I mean, in production today, in data centers, all 100% liquid cooled, direct liquid cooling, 100%, right? I mean, you walk into the Oak Ridge data center, it's all silent, except for one thing's on a corner, which is the file system, which is still spinning Rust, right? So, but apart from that, you walk in there, you can have a string quartet, and, it's like no noise at all, right? So it's kind of interesting, all these technologies are a lot of challenges in putting the systems together. Anyway, so this was sort of, the retrospective. Now I'm going to fast forward, and clearly I'm going to talk about AI. But why do I think this wave is different from the other one? It's because of the speed, right? I mean, this chart shows that effectively the speed at which AI is creating disruption is a lot faster than any of the other waves we have seen. I mean, this is an indication, but 100 million users in ChatGPT in, what is it, like 2 months, right? I mean, this is unprecedented, right? I mean, you remember the first picture when you're an innovator, you got time, well, is this an elephant or something like that? We don't, right? I mean, this is moving too fast. And that is the big challenge for the innovators here. It's also because AI is a pyramid, right? Where effectively only the few AI elites can play at the very top of designing and training some of the big models. Everybody else is living with the consequences of that. Is living with the consequences of whoever made the choices at the very top of training, designing, and building a new model because they have the data, they have the money, and they have the skills. Everybody else is thinking about either consuming it out of the box with a ChatGPT or whatever, Llama type things, or perhaps doing a little bit of tuning and something like that. But that's the problem, right? Because it is effectively very few players who can afford to drive the big changes, which was not true in many of the other waves that I talked about before. Now, this picture, I think Matteo showed a very similar one, is the growth of the models, right? So this is just a parameter size. I'm going to talk about compute in a second. But the models have been effectively doubling in size every year. Now, because all of you know that there's a quadratic relationship between size of a model and training compute to train the model, this means that the compute needs go up by a factor of 4 every year, which is kind of a crazy number, right? If you think of Moore's law and things like that. And when people say, okay, now we're starting to do small language models, yeah, of course, you do it because you can't afford to do anything else. But if you could, it slowed down a bit, but not much, right? I mean, the new multimodals and so on, they're still growing pretty much at the same speed. And people say, well, we have exhausted humanly generated text. Yeah, that's probably true. But there's a lot more stuff. People are using video. They're using DNA. They're using polymers. They're using proteins. They're using weather. There's a lot of other sources of information that can be used to train foundational models. And we're just at the tip of that. So it's become a supercomputing problem. I mean, again, also Matteo mentioned that all the new supercomputing centers are actually AI centers. And here's how I see it's become a supercomputing problem. Now, here I've moved now to training compute. These are operations needed to train a model. And we're talking about, the two eras of pre-deep learning and then kind of the foundation model era. Now, go back to like 2009, right? So this 2009 is the petaflop era, right? So it's when we broke the petascale boundary. Now, look at the largest model, which is some little bubble there. I forgot what it was, some word, feed-forward neural network or something like that. And then look at the capacity of let's say if I run the largest petascale supercomputer for a week, how many models can I train? In 2009, the largest supercomputer of the world could train millions of models, right? So at that time, AI was not a supercomputing problem, right? Because if my biggest supercomputer in a week can train a few million models, I'm good, right? I mean, I have enough capacity to be able to train that. Now, fast forward in 2022, and look at the very top of the chart there. So this is if I run all of Frontier, which is 50,000 GPUs, for 1 week, I barely have enough compute capacity to train one model, right? So that is a big change, right? Because how many people can afford to buy Frontier? I mean, the US publicly said this is a $500 million machine. You run it for 1 week, and it trains one model, right? This is the final training run of one model. So this is where I think we have a problem. Also, because most people cannot afford to buy Frontier, so a 1 week of an 8 GPU server, you're no, this is log scale, right? So we're 7 orders of magnitude below what you need to train these kind of things. So this is a problem, right? And it's a problem that, unfortunately, has several complications. One is that, when you're at the very top, systems tend to be extremely unreliable. So also training jobs, they tend to be really like a supercomputing job. They're not there are lots of people that have a lot of more capacity, but not in a single system, right? Because when you're running a training job is one job that spans across 50,000 GPUs. So the reliability and the ability to make that job continue without actually breaking too many times is important, right? Which is what supercomputing has been about. And unfortunately, many of these systems are not reliable. This is some data came out of a meta study where they showed that they collected tens of millions of hours on runs on their research clusters, and they're saying that their mean time to failure if I run a job over 16,000 GPUs is going to be 1.8 hours, which is consistent with some of the things they're saying. And then, if I imagine I need to run things on 100K GPU, these things are going to break every 15 minutes, right? So there's a big problem there on reliability that everybody's now jumping up and down. They're figuring out, okay, I need 100,000 GPUs to train. And now if you read the news a few days ago, someone saying I'm going to put $500 billion on the table for this Target project between OpenAI and SoftBank and so on. Now, 500 billion will buy you, roughly speaking, 25 million CPUs, which, by the way, is also 25 gigawatts. Kind of a different problem, but forget about that. But 25 million GPUs in one job, they're going to break every, 1 minute. So what are you going to do? Checkpoint every 30 seconds? Not going to work, right? So you got to start thinking about something else. It's also kind of challenging because if we look at the typical trajectory of, this chart shows a few different, scaling laws projected out. If you look at the trajectory of, where GPU performance is going to go, it's log scale. It's going to, or other similar accelerator technology, it's going to progress, but, it's not going to be as fast as needed to hit the new models and the compute capacity of the new models, right? This is a very optimistic assumption of where supercomputing system performance, which is effectively gated by the accelerator performance, is going to go over time. It's still going to be at in the order of 60-70% per year. Yeah, and we're looking at compute capacity and costs that are growing at 500x per year. Right. So this is the biggest problem, and it's become a luxury item, right? So to the point that, the joke in the community is people are, if you have to ask how much is it going to cost to train a model, it means you can't afford it. I mean, seriously. It's like, if you need to ask the price of a Ferrari, it means you can't buy it, right? And that's become, a game of, hundreds of millions or billions of dollars to the very top. And why is that a problem? Because, and this is something that, someone, I'm kind of borrowing this line of thinking, which I liked. I think we are in AI where we were in 1903 when the Wright brothers took their first flight, right? That was everyone's imagination. And now fast forward not too long after that, and, AI today is capturing our imagination of how this can change the way in which we live and work across the boards, and not just for the techies. All the young people are going to be, using AI, and they're going to be using AI to make their jobs better and things like that. But now imagine where we are today with aviation. It's like a lot of people can afford to, run a transcontinental flight at, a decent price. But imagine if we had a monoculture where only one or two companies were able to manufacture airplanes and run the airlines. I think this is the danger that we're facing today. The danger we're facing today is that there's an AI monoculture which is driven by investments that's going to cause a narrowing down of the players in this space, which I think we have, as a community, we have to try to fight, and we have to try to line all our investments into fewer bets, larger bets, to try to counter this potential AI monoculture. And I think, unfortunately, the whole wave of open source model, which is improving, isn't going to fix it, because honestly, they're all derivatives of kind of the Llama family, which is still pushed by effectively one single player out there, and nobody can actually afford to train one of these models anyway if we're thinking about the hundreds of billions of dollars, right? So I mean, to me, this is why I'm worried, and this to me why I'm hoping that communities like HiPEAC can really start thinking about this problem in a much more kind of focused way, right? And I'm hoping that, the mission for the next 20 years of HiPEAC is really going to be to lower dramatically the cost of AI. And I'm talking about not 2x, right? I mean, many of the community here is looking at, just the hardware layer. Okay, I'm going to build a better accelerator. No, we've run out of ideas over there. I mean, yes, most of the ideas were, I moved from 64 to 32 to 16 to 8 bits to 4 bits to 1.54 bits now with the ternary weights. We're not going to be able to go much lower than that, right? Those are one-off gains, right? One-time gains. We need to think about the whole stack. We need to think about, how can I dramatically lower by a factor of 1,000x the cost of AI so that I can make it a little bit more broadly affordable and accessible to a larger community of people that will fight, kind of this AI monoculture risk, which I think we're fighting everywhere. Here I'm just throwing some ideas, but of course, the whole stack is open. Can I train with fewer data? Can I, break the models, mixture of expert, combination of expert? Can I change the way in which I, train? Can I change the data formats? Of course, it's hardware. And then there's like the new crazy ideas. Can I do, neuromorphic computing, analog computing, or something like that doesn't require CPU or GPU? So here's kind of, my mission for you for the next 20 years. And I'm hoping that, I've given you an idea of the waves I've seen, the waves I'm seeing, but this is a new one that is going to be a lot faster and a lot more disruptive than many of the things we've seen. Thank you.